This lab investigated how pulleys affect acceleration in a system of connected masses using the Atwood's machine. Um, it's basically a representation of the classical pulley problem. This setup will also let us measure speed and calculate acceleration, but also the pulleys will reverse the direction of force. This paper by Semurumi shows how real-world imperfections um, can affect how accurate our acceleration measurements are in the Atwood's machine setups. It also highlighted how pulley friction resists motion, making the acceleration that was measured to be much slightly lower than the theoretical value, meaning that systemic errors are bound to exist. An elevator is a good real life reference given that it's a pulley system that lifts and lowers the elevator, or it's also known as the cabin, where the cabin goes up and its counterweight goes down.
So the materials for this experiment were the Pascal/Capstone application software, along with this hardware that we see in the picture, two pulleys, weights in grams, and a laboratory notebook and laptop for observations.
For the procedure, firstly, we chose two different masses to be used in the trials to determine our theoretical acceleration. Then we turn on the sensor, set it up, and place the masses on before pulling it down and letting it go. From this, we calculate the experimental acceleration and we calculate the percent error between theoretical and experimental. Next, we combine the power of two pulleys. We selected two new masses that are greater than the first masses but also do not have a very absurd difference between each other. After this, we run the experiment until getting a straight line where we can calculate the experimental acceleration and calculate the percent error between the theoretical acceleration of the two new masses and the experimental acceleration of this new trial.
Okay. Yeah, you can go.
So to start off this lab, we first found the theoretical acceleration before we connected our graph or anything. So we picked our masses, which was mass 1, which is 80, and mass 2, which is 10, and then our gravity, which is 9.8 meters per second. And then to find our theoretical acceleration, we use that formula that acceleration equals m1 minus m2 plus divided by m1 plus m2 times gravity. So when we plug that in using our masses of 80 and 10, we got 7.622. So we rounded up to 7.63 meters per second squared. And this is just the first table we created from our theoretical acceleration. So after we had found our theoretical acceleration, we moved to our step one of the experimental development. So we passed the string through the pulley on the Atwood's machine, and then we made sure that their M1, which was their 80 mass, was in a higher position, and then we let go. Oh, there was no recalibration, so we just made sure we were steady before, and then we let go. Um, and the sensor caught and created the graph that we see here, the top one. And then based on that graph, which is our speed, linear speed, we then found our acceleration, our linear acceleration. And then as you can see, like when it started going up, acceleration increased. So we annotated our graph to match the increase, and then made sure it showed on the top where it was the speed, and then the bottom where it was acceleration. And then we found a point. It was our 2.6 acceleration. And then our speed was 2 meters per second. And this is just a picture of our graph created and annotated. And then this is a screenshot of our same graph. We just zoomed in so that way we could better see that the acceleration was going up and the speed of what it was, which was the 2.0 meters per second. So step 2 of our experiment was again to find the theoretical acceleration, but this time we would change it to 2 pulleys rather than just 1 pulley. So we had to change our masses, and our new masses was M1 is 95 and M2 is 15, and our gravity stays the same of 9.8 meters per second squared. We used the formula that A squared, the A2 equals the minus 2m2 minus m1 over half times m1 plus 2 times m2 times gravity. So using that formula, we found our theoretical acceleration of 8.22 meters per second squared. And then to minimize the error caused by friction and the factors, the inequality between them had to be more than 50 grams. So that's the M1 minus 2 times M2 has to be greater than 50. And then it was a 65. And then from there, we moved on to the second phase of our experiment. And then following our theoretical acceleration, we created our third table, which was our theoretical acceleration for 2 pulleys setup. So again, our M195, our M215, and the theoretical acceleration that we found was 8.22 meters per second squared. So afterwards, once we found our theoretical acceleration, we set up for our actual experiment again with the 2 pulleys rather than just 1. So once we set up for the pulleys, our M1 was under the first pulley, and then that was our 95 weight, and then would go up to our second pulley, and afterwards that would have our M2 weight, which was 15. So once we had set it up, we went ahead and used the capstone to record once we let it go, how it went up and hit the first pulley. And then that's our first graph, the top one, our linear speed that was created. It is more or less a straight line that shows it's increasing. And then based on that, we use the capstone to find our linear acceleration. So once we found our linear acceleration, we went ahead and annotated it. In our annotation, it shows that as it was increasing at the time mark of 2.69 seconds, our acceleration was also increasing at an 8.22 meters per second squared. So when we further examined it, it showed that, yeah, it did match our theoretical acceleration of 8.22, and our graph matched. So again, this is just the same graph, it's just zoomed in. So for our speed, it was 2.69, and then our time was 0.357 seconds. So it just shows like the connection from the 2.69 speed to the 8.22 acceleration. So following our graphs, we were able to calculate and find our experimental acceleration from our exact experiment using the pulley and then the capstone. So this is just our table 4 showing the experimental acceleration for the two pulleys set up by percent error. Again, our experimental acceleration was 8.22 meters per second squared. And so our percent error is 0 because we matched it exactly to what, or it matched exactly to what we had theorized was going to be the result or the acceleration. So our step 4 after this was find a combination of masses that gives you the closest acceleration to 0. So for that, you need a combination of masses that result in the net force of the system being as close to 0 as possible. So we would be following, or according to the Newton's second law of motion, the acceleration of an object or system is directly proportional to the net force and inversely proportional to the total masses. So the equation for that would be acceleration equals net force divided by the total mass of the system. So the only way to achieve acceleration of 0 is that the net force must be 0 as well. And then that's only found when the gravity or the forces on, which is gravity, on the mass are equal to each other on both sides. And then that only happens when the masses are equal. So both of our masses would have to be exactly the same for our acceleration to be 0. And then again, it would be us running the experiment, and then going from there based on the graph that we get. But of course, like right now with our experiment, we found no percent error, so we were able to find it exactly. But there's no guarantee we'd be able to find it exactly when we conduct that experiment as well.
In this lab, we explored the principles of an Atwood's machine and how changing the setup or mass distribution affects acceleration. By experimenting with both a single and double pulley system, we learned how force and motion are related, and how the direction of force can be inverted using pulleys. This lab helped us understand how theoretical and experimental results can differ due to real-world examples like friction and pulley balance. And overall, this lab demonstrated how Atwood's machine models Newton's laws of motion and allowed us to apply concepts of acceleration, tension, and system dynamics in a practical setting. So, going on to the questions, considering the percent error you are used to having with the motion sensor, is today's percent error greater or smaller? Why? So, it's smaller, which could be due to the motion sensor capturing a shorter distance and the setup is moving downward rather than farther away. Between today's two setups, which have a more significant percent error. So both of them were actually 0 and pretty minimal. So both experiments ran smoothly. And that's it. Thank you.